Alright, MT114, metal rolling processes. This is going to be our second video, second lecture on this topic. So in this lecture, I'm actually going to look at more the differences, what metal rolling is, we're going to review, and we're going to look at the differences between hot rolled and cold rolled. Hopefully you've gotten some idea of what rolling process is after watching those videos last week. For last lecture's videos. I usually show those processes during this PowerPoint presentation. Instead of doing that, I've split it up this time just because the presentation is a bit different. So hopefully that goes over well. It looks like it's working out pretty well. So moving on into metal rolling processes. Alright, so just a review, what is a metal made of, right? So we discussed this in the previous lectures. So we looked at the crystal structures of metals, how they stem from our crystals of either body-centered cubic or, in this case, face-centered cubic, right? So we have these atoms on the faces of our crystal structure cube, and that crystal structure cube patterns out until you get to grain boundaries, right? And then we end up getting our metal at microscopic, under the microscope, looks like this right here. So we end up getting our crystals and the different grains in our crystals, which results in deforming of the metals, right? So we think again of these as our atom crystal structures with our lattices, right? So those slit planes along the atoms. And we talk about deforming metals. So elastic deformation is reversible since the material yield strength. So if we don't hit, so our elastic, so talking about our stress strain curve, two of the biggest ones are elastic deformation and plastic deformation. So when do these start occurring? Well, elastic deformation is all along this loading line here. So this is how much stress over how much it's straining. What that means is how much loading are you doing versus how much it's actually stressing, or stretching, rather. So what actually occurs with modulus of elasticity tells you how much it's actually going to stretch with each amount of force or what certain amount of stress applied to that. So you can calculate this. Stress is force over area, cross-sectional area. We'll actually get into that later. But this would be plastic deformation. Plastic deformation would occur after our yield strength. So we have elastic, so meaning if we unload this, it would go back to its original shape. After this yield stress here, so after this here, we'll actually end up stretching plastically. So when it starts stretching plastically, we end up getting this slip along our lattice. So that plane there of the atoms. And when that starts stretching, that doesn't go back to the original shape. So that's where the deformation of metals happens, right? And why that's important is because we're going to be talking about rolling, and in a bit we're going to be talking about work hardening. So you saw the rolling process, so I imagine you understand this pretty well. But the process is plastically deforming the metal by passing it between shaped rollers, right? So you're trying to shape it in a certain formation, either a sheet or in this case a rod, sheet or a rod here. So we have different rollers for each situation, right? And we're actually deforming that plastically. So the rolling processing in general for metals, so this accounts for 90% of all metals produced in industry. So it's rather big process that happens out in industry. So good to know about it, especially for engineering. So rolling allows for high production rates and high dimensional accuracies. So cold rolling, cold working, you'll tend to find that you end up getting a high dimensional accuracy, meaning you're not going to get, so what that relates to is, say, hot working, for instance, you're going to get deformation or shrinkage as your part cools, right? Just like anything with heat and temperature, you get an expansion and a contraction of material, right? It's going to change its shape just slightly. So the rolling process used to create sheet, strip, beam, columns. So this is a diagram in the book. I'll let you read this in the book more so than I put it up here for an example of all the different processes that are used with our rolling process. So you can go from a slab, a billet, and a bloom to all these various different products here. And as you go down the line, you can split off into, say, 2 other groups or more. But these are the main, say, building parts that are used. So you can see I-beams, structural beams, rails, parts that are used widely across a lot of different industries. Flat rolling process. So it is important to note that during the flat rolling process we get a varying velocities. So as we reduce the thickness of our metal, we actually get a different speed of the material going in versus the material coming out. And there's an interesting video. I'll point to the video. I'm not going to necessarily show it right now, but you can actually see in a lot of the rolling processes, as something's rolled, it actually moves quicker out the final exit of the rolling process. So you have initial velocity and then a final velocity. And why this is important is because this can actually depict what your surface finish is actually going to end up being. And also you can end up deforming the material if you end up rolling it at various different rates. But really is the big thing is surface finish. So there's this thing called forward slip. Forward slip is the ratio of the difference in the wheel speed to the final strip speed. So we have VF here minus VR. So our VR here is the velocity of our roll, tangent basically to that roll. And we want to see what the velocity or versus the velocity of the exit of the material. So we're looking for a forward slip. So that's what a forward slip ratio is. So this is important since forward slip is directly related to, as I mentioned, surface finish. So a lower forward slip value actually is preferred over the higher values. So you get a better surface finish the lower this value is. So the closer of these two that you can get the final forward speed versus your roller speed, or final rolled material speed versus your actual roller velocity. So the closer those are, the better your surface finish will be. Alright, so when we're talking about rolling forces, so we want to figure out what amount of force, say, we need to actually roll this material through to deform it, right? So the force needed in this case would be calculated using this equation, and this is off of our Young's modulus, the average true stress of the slip in the roll gap. True stress of the strip in the roll gap. Actually, it might not be. Sorry, I saw Y average. I was thinking it meant Young's modulus. In this case, it's the average true stress of the strip in the roll gap. So, what is the true stress of this strip? Yeah, I worded that weird apparently. But basically, this strip of material that's coming through, what is the average true stress of that? And I would have to look, but I think it might be referring to that yield strength, because that's when it's going to deform, right? And then this is the width of the strip, and the roll strip contact length. So what is the roll strip's contact length? Meaning our contact length here, and I think we can see that here. So L, our contact length, where are we actually touching our roll to our strip itself. So multiplying that out would give us, well, how much force we actually need to push on this. And that would be needed for calculations on various different materials. You know, as the material changes, obviously the force is going to have to change for that. So the machine is going to have to either increase or decrease the amount of force being used to hold those rollers in place. Alright, so gives you an idea how to find, say, the roller force, say the rolling torque now, the power requirements needed for that. So now we want to figure out, alright, so we know how much force we need. Now how much torque do we need to actually roll those rollers to actually move that material, right? So the force previously calculated we use to actually find the torque. So the torque essentially is going to be our force, so the force we apply here, times this distance A. So if you notice, this force that we're actually applying is going to be around where our average or midpoint between our contact length is. So this is what constitutes for torque, right? So you have a torque wrench, it's a distance, a force times a distance, right? Also called a moment. In this case, this creates a torque for the motor to have to turn. So that's the exact force the motor has to overcome to turn this this machine to roll that roll, this material through the rollers. So you end up getting force times that A distance. So A is from this and the distance here to the center distance of the rollers, and that would give you a torque. And we're not going to actually go into, I'm not going to necessarily require you to calculate this out. I'm just going through the process an engineer would have to go through to making this. It's really good to see basically what an engineer does. You'll be doing these calculations. We get into machine design a bit more, as well as some of your other courses that you take with Jeff. Strengths and materials, statics, for instance. Rolling is a multi-stage process. So we actually saw this in one of the videos. They talked about the various different rolls that are used for the rolling process. So what we have here is just a view of various different types of rollers. So it says for A here, just our typical roll. This is actually how we'll do our rolling in lab. We just have two basic rolls and we'll have the material that goes through. So this is a 2-high mill. If a 2-high mill is used for a thick but short work pieces, it will commonly roll a billet back and forth in multiple passes. So for instance, if we want to take this down multiple stages here, we'd roll it back and forth. In lab, we'll actually just roll it through. We might try rolling it back and forth, but we'll talk about that in lab. There's some issues we have with our roller. All right, our B site high is 3-high mill here with an elevator for multi passes. So we'll go through one and then through the other. And why does it do that instead of going back and forth? For instance, you have a larger piece here, right? So it's a higher cross-sectional thickness as it goes through. And then we have a different thickness material that has a different thickness between the gaps, right? So you can have a 3-high mill for that one. Typically all meant for multiple passes, right? C, 4-high rolling mill. So various features on this, but what you end up seeing here is you get backup rollers, and this helps with the stiffness of the rollers themselves. So you actually get some bending of the rollers, and we'll actually look at some defects, I believe, in the next one of the next slides here. This one's kind of neat. Planetary rolls. So if you have rolls rotating around, say, a larger roll, you end up getting planetary rolls. So kind of how planets rotate around the sun. And then I think the last couple here. So this one you saw, I believe, in the video. They go from just multiple passes here. So that one's tandem rolling. So it has 3 stands, and every pass it'll go slightly thinner. And then the last one here, cluster mill. So we have backup rolls that basically apply a force, and you go down to essentially a small strip, and you're getting a very thin piece of material. So this is a way to equal out the force, get an even force on our rollers here. So those are the various different stages. Seamless tube processing. So this is pretty interesting, and this is used for various different types of, say, seamless tubing that you might see for piping, oil piping and different things. But the way you actually make the seamless tubes is rather interesting. So you actually have, say, 2 plates, right, and your roll goes in the center. All you have to do to create a cavity in here, so a cavity that essentially a hole all the way through the cylinder that you're sending through, is you take these plates, put a rather large amount of force, especially for steel, so you have to have a rather high amount of force. And then you take one of these plates, or you take the plates and basically roll them back and forth, and eventually that rotation develops this hole in the center. Kind of an interesting thing that just happens, physical property that happens to materials. And then you would take, to expand that cavity that you created, you would take a mandrel and basically shove that into the whole cavity that you made. And then you take 2 more rollers, and basically sometimes they're pulled through, sometimes that material is pushed, or kind of pulled by the rollers. But what that tube does is they create a specific thickness between the mandrel and the rolls, and you end up getting your 1/4 inch thickness wall tubing, or the various different gauges to the piping that you would get. So that's how they end up making a lot of the seamless tubing. It was one of the interesting processes that you actually see in rolling. Structural H-beam processing. So this is one of those staging, possibly one of the tandem rolling processes that you might see out there. You have a blooming rolls. So what you end up seeing in this process of, say, reason why you would have a tandem mill, various different roll processes, is because you might have stages, right? So here we have a stage we need to get to plastically deform the metal enough, but not too much. Because if you do it too much, you end up screwing out the material, which we'll look at defects in a minute. And as you go through the process, you end up deforming the material in another way. And eventually you get down to the thickness and the dimensions that you were looking for. And that's a typical rolling process. H-beams is, really one of the big ones you end up seeing out there. Rolling threads versus machine threads. So you can actually get various different properties with rolling versus, say, like a machined thread. So if we think back down to how the atoms are formed in the material, those crystal structures are formed, we think about those slip planes, right? So with those slip planes, we end up having the same pattern of, well, you can think of it, I know they're at atomics level, they're all different directions, but in this case what they're showing is there isn't any work hardening done to it. So the machine, for instance, that cuts this, cuts it right off, right? It's not really doing any work to the material. So when we actually work a material, which we'll see in this cold rolling lab we'll do this week and next week, we actually get a deformation of the material, which actually hardens the material. So what you actually have in the rolled threads is a bit harder material, as well as a worked surface. So you would have less of say a stripping of the threads would be less likely. At least it would have to take a lot more force to do so. So you end up getting, again, a better property depending on how, say, even a thread on a bolt is made. It's a rather interesting thing to think of, especially if you're designing a product and you see a rolled screw versus say a machine screw. What's the difference, right? Alright, so hot rolled processing. So typically hot rolled processing, we have we talked about hot worked versus cold worked. It's above its recrystallization temperature. So what that means is it actually recrystallizes at multiple stages, and we'll look at that a little bit more, especially when we get into heat treatments. But at different stages, there's different types of crystal structures. So it might go from body center crystal to face center crystal structure when it heats up and cools down. So it is actually at a different crystal structure form in this stage. So it's above its recrystallization temperature. In order for steel to be formed, rollers must exert force of several thousand tons. So in this case, what'll happen is it gets easier to work, right? So that is one advantage to hot worked pieces. You don't necessarily have to exert as much force. So hot rolling has a pretty big advantage in that manufacturing process. But as I mentioned, with that recrystallization, you end up getting a different, basically, crystal at the end. You get a recrystallization of the material. And this could be a good thing, this could be a bad thing. It depends on what you want in your material. And this is, again, why it's important to understand what the difference is between hot rolled and cold rolled. So we have hot rolled metal here. You can actually see is held above its recrystallization temperature. So you have the wrought product with large grains. And what happens is in the deformation process, you can see they get stretched, right? They get stretched and the crystals are all deformed, and there was actually some working done to the material, but it's still at that temperature where you'll get new grains forming. So new grains will actually form and regrow in place of these long elongated crystals as it cools down. So that's why it shows here as it goes through its cooling phases, you end up getting new crystals. So hot rolled grain changes basically the properties of that material in its final phase. Cold rolling, cold rolling metal causes strain hardening. So for instance, when we look at cold rolling, we get this same stretching, except for it's in its final cool state, right? We still get this stretching of materials. And what that does is it does the thing called strain hardening. So these are things that change the mechanical properties of the material. So we talked about this in our first lecture, first chapter 1 material. I believe chapter 2 we discussed this as well. But cold rolling mechanical changes the metal. It increases hardness and stiffness, so puncture resistance increases, bend resistance increases, so it's stiffer, right? It's harder to bend. And you get a reduction in cross-sectional area. So for instance, if we take a hammer to a piece of metal and we hammer it, that metal will actually deform and become thinner in the direction I'm hammering it. And you'll get a reduction in ductility. So we obviously change the shape, and we take that ductility and basically, since it's stiffer, it's less likely to bend, right, and stretch. So it might get harder, but it typically gets stiffer, less ductile. If you ever want an example of this, one easy way to do that is take a paper clip and try to bend it back and forth in the exact same spot. You can actually, a lot of times you can see the material change color. It'll become like a whiter color. But you're actually changing that material there, and you're changing that I guess strain hardening, changing that crystal structure by moving that, basically overcoming that yield point, right? So your strain hardening, here's that example with the rollers for cold working. So if you cold worked something, you've strain hardened it. This is a phenomenon which is by ductile metals becomes harder and stronger as it plastically deforms. And this is why you see, a lot of iron working. Where they're working making tools, they're typically hammering out, say, a sword or some piece of material. They're actually working it, making that stronger, harder, better for, say, a tool, right? So in this case, we end up getting this elongated grains, right? So we cold worked it, we've deformed it, it's still deformed, it hasn't regrown crystals, so cold worked. And that's really the big difference between hot worked and cold worked. So why does it become harder, right? So that's really gets into those dislocations we talked about in chapter 1. So at the atomic level, we get, say, a missing atom. We end up getting what's called a dislocation, essentially an imperfection in the crystal. So here strength is increased by making these dislocation motions difficult. So what happens is when we get multiple dislocations next to each other, they already don't want to move, right? There's this atom here that just doesn't connect to anything, and it puts a stress in the material. So if you have two stresses next to each other, they end up repelling each other. They don't want to pass each other. So this is what really causes, that plastic deformation causes these dislocations to essentially become entangled, which ends up increasing the metal's strength. So here's an example, and I'm not sure if I showed this picture already, but basically you can think of these as the entanglements. This is, I forget what they mentioned, titanium alloy after cold working. So they took titanium alloy and they worked it, cold worked it, and then they polished it and basically took a 0.9 micrometer view of this. So that dimension here is how far it's zoomed in, and you can actually see those dislocations. So once those dislocations become entangled during cold work, it's really difficult for those to pass each other, to move. And what you end up getting, you can kind of think about the whole stick reference. You get a bundle of sticks, it's really hard to break, right? One stick's real easy, but if you get a bunch of those together, it gets a lot more difficult to break or bend, right? So that's kind of the ideology I like to think about for those dislocations and what cold working it really is. All right, so we can see material properties change when we do a percentage of cold work, and that's what's really going to be this week's lab, is going to be looking at what cold work does to a property. So here we look at 3 different materials. So we have a steel, we have a brass, and we have a copper. And as we do work, we end up seeing the yield strength. So we talked about that yield strength, where that ends up starting to plastically deform, right? We'll see that yield strength go up. So as we plastically deform the material and cause that to cold work percentage to go up, we'll end up seeing that yield strength where it starts plastically deforming go up. The tensile strength again goes up. So ultimate tensile strength, the max amount of stress that material can hold, will actually increase. But what you see is a massive drop in ductility. So again, breaking that, or essentially bending that, will end up breaking it a lot quicker, right? So it won't stretch as much. So that gives you an idea for material properties. And we'll look at here in a minute. I might make it our actual second lecture this week. We'll do a calculation on how to essentially figure out what your yield strength, tensile strength, and ductility will be after a rolling process. So you know it before, and then what is it going to be after I change it by this much, right? After we plastically deform it from 1/2 inch to 1/4 inch, what what are we going to see for a material increase? So we'll actually look at a calculation for that. Sorry. Going on, residual stress developed in rolling here. So we mentioned this before about work hardened pieces having internal stresses, right? So one thing you'll tend to see with cold worked metals is they aren't as widely used. Well, they're used quite a bit, but they have the drawbacks when you're machining them. And what I mean by that is, say you could see the forces in this are going to cause this to, say, want to flex in a certain way or bend in a certain way, right? So if we actually took this on a machine and, say, just took the top right off here and just took an end mill and took that right off, you know, what we're going to actually see is we're going to see this metal bend. It'll warp a little bit, and this is really important, especially for those high precision projects that you might be doing in engineering. You know, they might have several thousandths of an inch as say a tolerance on how much, or flatness, for instance. And if you're using cold worked material, and you cut something like that, face it off, and remove, say, the top of this off, you'll actually see a flex in the material. And it might be subtle in some cases, but might be enough to throw off, say, a sensor. So it's good to know, again, for machining purposes, how would you go about dealing with that, right? And there's this relieving residual stresses. So this is called annealing. So typically annealing is conducted after cold working. So you cold work a material and then you want to get those new crystals grown, right? So you want to remove those internal stresses, those things that'll end up causing your material to bend and flex as you machine it. So you would take that, put it through an annealing process, essentially heat it back up in an oven, let it go to its recrystallization temperature, and then let it grow new grains. And then depending on what you want those final properties to be, would really give you, or it would basically cause you to cool it in a specific way. And that all gets into material science, and we're not going to necessarily talk too much about cooling times and various different materials. We'll look at some of that when we get to heat treating, but we won't get too far into that material processing. Alright, cold work strengthening. And I think this is where I'm going to cut this video. We're going to pick up at this. This is that video, that portion of the video I mentioned. We're going to do how much cold work we've actually done on a material, and then we can see what our final results going to be from that. Alright, so I'm going to stop it here. Again, if you have any questions on anything that I've presented here, please ask, send an email if anything seems unclear. Otherwise, I'll see you either in the lab this week or be talking at you in another video here soon. Alright, later.